This is the Cobalt bomb. And it is a weapon that could have ended the world as we know it. Unlike traditional nuclear weapons, the Cobalt bomb, part of a family of weapons known as salted nukes, had a hidden secret that could quite literally take out the whole world in one fell swoop. And how it could do that will both surprise and scare you. When trying to understand how salted nukes work, they're actually pretty complicated since there are really 4 parts: a regular bomb, a fission nuclear bomb, a fusion nuclear bomb, and the salt jacket surrounding the fusion core. Each of these parts must happen exactly at the same time and create the right conditions, otherwise the salted nuke will fizzle out and not work properly. The first step in detonating a salted nuke is by blowing up the conventional bomb and starting the fission reaction. Inside the fission core are elements such as uranium-235 or plutonium-239 and are the key source of fuel for this part for a few reasons. First of all, they're radioactive, which means that when they split apart, they release huge amounts of radiation and power. The second reason is that these elements are heavy and have a large surface area. Because of this, when the conventional bomb goes off, there needs to be a good chance that the atoms will hit one another and split into other atoms. The last reason is because of something called critical mass. Because there can't be an infinite amount of material in a bomb, as well as the constraints of nature where elements like uranium-235 and plutonium-239 are very rare. Only relatively small amounts of these elements are necessary to ensure a proper fission reaction. The next stage of the process, known as fusion, is more complicated than fission. Why the fission process is needed first is because the intense heat and pressure it generates will be the force required to start the fusion process. Inside the fusion core are several isotopes of hydrogen, such as deuterium and tritium. Because these particles are very light and small, it's much easier to fuse them together as the intense heat and pressure from the fission reaction create an infinitely smaller space inside the fusion core. As a result of this, the bomb will create massive explosive energy measured at a scale of millions of tons of TNT versus thousands of tons like in a traditional fission bomb. With all that energy now flowing freely from the fusion core, the last stage in the process is what makes a salted nuke different from every other kind of nuke ever imagined. Once the fusion core begins to react, the intense heat and pressure will cause hydrogen atoms to fuse together. As these hydrogen atoms fuse, they let their extra neutrons fly into the jacket surrounding the fusion core. These neutrons will then convert the non-radioactive metal into essentially an atomic grenade. In the immediate explosion, the jacket will shred into a fine radioactive mist that gets dispersed with the blast and wind that carries the now radioactive particles into the environment. The material will then salt the earth and make it unlivable, much like the ancient Romans supposedly salted the land of the defeated Carthaginians to punish them for generations. But what is this jacket made out of? Of the various materials engineers can use, there are 2 main considerations when picking one: abundance and ability to absorb a neutron. This is because there needs to be a huge amount of material to comprise the shrapnel in what is basically a giant radiation grenade. Additionally, this material needs to be easily converted into a radioactive isotope. Among all the elements of the Earth, things like gold, zinc, and cobalt are among the best candidates, and this has to do with their half-lives. Half-life is the amount of time it takes half of a radioactive element to decay into something else. This generally means that the element will decay into a byproduct that is not radioactive, but not always. Because of this, half-life is an important consideration when building a weapon to maximize nuclear fallout. Materials with a short half-life will make an area livable much quicker than in an element with a very long half-life. Salted nuke elements like gold have a half-life of just 2.7 days, while zinc has a half-life of 244 days. However, these elements' destructive power pales in comparison to cobalt's. You probably don't realize it, but you interact with cobalt practically every day in your normal lives. Cobalt is a relatively common metal, from the iPhone in your pocket to the engines of aircraft you fly on and inside of some hospitals. However, don't let its innocuous uses fool you. Under the right conditions, cobalt can be transformed from your quiet, nice grandma into a killer hiding in wait. This happens through the fusion reaction in a hydrogen bomb. When it goes off, the fusion core releases neutrons that bind to the naturally occurring cobalt-59 and turn it into cobalt-60. By adding this extra neutron, the nucleus of the cobalt atom becomes unstable, thereby making it radioactive. But this radioactivity is much more severe than that of other salted metals. Cobalt's half-life, once it becomes cobalt-60, is about 5.3 years, and the radiation it emits is enormous. To put this into perspective, let's examine a quick hypothetical to show you just how deadly cobalt-60 really is. To emit a radioactive energy of 1 curie, there would need to be about 0.88 milligrams of cobalt-60. If a person were standing 1 meter from the cobalt unshielded and unprotected by anything else, that person would absorb 12.96 millisieverts per hour of radiation into their body. After being exposed to this level of radiation, one would have been exposed to the equivalent of 4 years of background radiation. After 1 day of exposure, you would start to feel nauseous and exhausted, since you would have experienced more than 5 times the annual radiation limit of people who work in radioactive environments. But the problems soon become worse in a week and longer. Once exposed to just 0.88 milligrams of cobalt-60 after less than a week, you would feel incredibly sick as a result of acute radiation poisoning. And if you continue to stay in the irradiated area, you'll probably be dead in a matter of weeks. While you may be wondering how it would be foolish just to stand next to radiation, you would be right. However, in a scenario where a bomb like this went off, the weapon should use between 1 to 5 tons of cobalt per each megaton of yield. That's about 5.6 billion times the amount that could kill you. Because of that, it's practically impossible to avoid coming into contact with radiation from this bomb. Which is why this could have literally ended the world, as seen in the famous Stanley Kubrick movie, Dr. Strangelove. In the film, an overambitious American general decides to preemptively attack the Soviet Union with nuclear weapons, since he falsely believes the Soviets have poisoned the American water supply system with fluoride in a communist plot to take over their bodily fluids. To stop this supposed communist takeover, he sent a squadron of B-52 bombers armed with nuclear weapons. But there's a problem he's not aware of. Unknown to the Americans, the Soviets had created a doomsday machine made to blow up if the Soviet Union were ever attacked. And the worst part about it, the device is salted with cobalt, meant to irradiate the world forever. Unfortunately, the movie's protagonists are unable to stop the attack in time, despite the hilarious sequence where we see Major Kong ride a nuclear bomb to the ground like a raging bull. The movie's ending is no laughing matter. The Soviets detonate their doomsday machine, and the end of the world ensues, not necessarily because of the blast, but because of the fallout. And despite the movie being a parody, a single powerful cobalt bomb could end life as we know it. For example, if the US were to detonate a bomb similar to the yield of the Castle Bravo test, which was the largest nuclear device the US ever detonated with a yield of 15 megatons, this bomb would be more than enough to irradiate the Earth through the jet stream. The jet stream is a series of very fast-moving high-altitude air currents found in the Earth's atmosphere that help regulate weather patterns around the planet. During the Castle Bravo test, the mushroom cloud reached a maximum height of around 130,000 feet. At a height of around 20,000 to 50,000 feet, the jet stream is well within reach of a cobalt bomb's deadly radiation fallout. So even if a cobalt bomb went off on another side of the planet, the jet stream would carry the highly radioactive particles over a matter of weeks, months, and years that would deposit them worldwide. If this were to occur, large-scale crop failure, mass deaths of animals, and the destruction of most drinking water would surely occur as civilized society disintegrated. For those humans that do manage to survive, they would quite literally find themselves in the post-apocalyptic world made famous in movies and video games, with no law and order, no food, no hope, and no future except for the next day. Bye for now.